So the second lecture for this week, and the last thing that we have managed to obtain is TDS, and here we have f.dx, right? Which we can basically write, so d is dds minus p dv plus sum over I mu I dni. Another thing that we have obtained or postulated more importantly is that we have the first law, which is conservation of energy. Conservation of energy. And two is the principle of maximal entropy. Okay. This is the point where we stopped on Sunday. And I would like to continue trying to deal with this equation and expanding a little bit this principle of maximal entropy. Okay. Now, this is already something which is good because, right, we have an equation, a mathematical equation without all those different indexes of full differential or not full differential. This equation is already nice, well-defined, mathematical. We can apply a lot of tools of calculus and analysis for this equation, which is basically appeared from this guy over here. This we'll use in a little bit, but let's first play a little bit with this equation over here. Okay. Now, another thing to remember, what we mentioned is that energy is an extensive quantity. Okay. What do we mean by this? So I told you that if I add to a system together, the total energy is basically a sum of those two systems. I enlarge it by a factor of lambda, it goes to from E to lambda E. Okay, so my question is, if my energy is a function of S, right, is a function of entropy from this equation over here, and is a function of all different quantities that or extensive quantities, which can be the volume or the number of particles or whatever I like. Okay. Now, why do I tell you that E is a function of S and different x's? Because I can look on this equation over here and it's a differential of E, and on the right hand side I have the differentials of the variables that E depends upon. Okay, so the variables that E depends upon is S, V, and N, or generally speaking, S and all the different other generalized coordinates, which are all extensive. Okay. So now I'm asking, what happens if I multiply the size of my system by lambda? Okay. So if I multiply the size of my system by lambda, I know that S is multiplied by lambda because it's an and X is multiplied by lambda because it's an extensive quantity. Okay. And basically I can work it out and say, well, look on this guy. This means that d lambda E equals to, or I'm sorry, this mu time E prime is T d of lambda S plus, or I'm sorry, minus P of d of lambda V plus sum over I over mu I d of lambda Ni. Okay. All of those lambdas I can get out of the different differentials. Okay. And I have lambda T ds minus lambda P dV plus sum over I where I have here lambda mu I dni, okay, which is simply lambda of t ds minus p dv plus sum over I mu I ni dni, sorry. Okay. And dE prime is simply lambda dE, okay, which can tell me that E prime is lambda E. Okay. So this is the property of extensive quantity. Even if I haven't told you that energy is extensive quantity, by simply saying, look, E is depends on extensive quantities on their own, so S and X, and I have this specific form of the differential that describes me the energy, or the differential of the energy, I will still get this extensive property for E prime. So I enlarge my system by a factor of lambda, the energy grows by the factor of lambda as well. Okay, so this is the property of extensive energy. Now, why is it helpful? Now, as I told you that I can use different theorems of calculus. Now, in calculus, there are many nice theorems for what is called homogeneous functions. So, I remind you, you probably learned it in your first year. So, G is a homogeneous function of order M if G of lambda x equals to lambda to the power of M G of x. Very nice. So now I can do it also for many variables. So G of lambda x lambda y equals to lambda m G of x and y. Okay. So I increase all my extensive variables, and here there are simply coordinates, right? I increase them by a factor of lambda. This lambda gets out as a prefactor to some power m, and m is this order of homogeneity of my function. Okay, so why it's interesting? First of all, we do see that in our case, we increase all the different variables by a factor of lambda, and lambda gets out for the energy as a prefactor to the power of 1. Right? So we do know that energy is a homogeneous function of order 1. Now, there is a nice theorem of Euler theorem for homogeneous functions. Homogeneous functions of order 1. Okay, and what it says? Who is Euler? Yeah. Very smart guy, almost as smart as Gauss. Okay. He was a Swiss mathematician, and he contributed a lot to mathematics, physics, graph theory, etc., etc. Huge amount of works. Okay. I'm pretty sure you heard about Euler by this stage. Okay, so if G of x1, x2 up to xn is a homogeneous function of order 1, function of order 1, which means that G of lambda x1, lambda x2, lambda xn equals to lambda to the power 1 of G x1 up to xn. Okay. then g of x1, x2, up to xn equals to sum over I from 1. Let's do it r, because we have already n, right? Let's do it r. R and r and r, because n is our composite variables, right? The number of molecules or the number of moles. So I goes from 1 to r of dg to dxi, while I'm keeping all the other particles, all the other variables constant. Okay, so for all j that is not equal to I, xi. The moment that I have a homogeneous function of the first order, Euler proved that this is the only form that this function can take. Okay. There is a proof. You once learned it. If you're really interested, I can rewrite this, the proof of this formula, but that's really critical for us right now. Okay, so what does it mean? For energy, we know that it's a homogeneous function of the first order, and we know that dE equals to TdS minus PdV. Okay, or let's write it down, plus F dot dx. Questions? Any questions? Yes.
יש לנו עוד סכום נוסף פה בתוך החלק של הסכום של נהיה 1 שווה, נהיה n שווה 1 עד r.
So the question, are there any other summations? No. No other summations.
So why do we write for every j that is not...
So the constant is I'm taking, this is my variable, and all the other coordinates are constant. That's it.
Summing on I.
I'm summing over I, so for any I, I'm taking all the other variables as constant. That's the only thing that it means. Right?
So you're just summing all the other j.
All the partial derivatives multiplied by the coordinate.
j ששונים מ-i, ואז עושה את זה לכל ה-i.
Yep.
Okay, so.
Okay. Yes.
לambda למטה זה בחזקת r.
1. So it is simply 1 over here, or let's not write it anything. Okay. This is the definition, right? So homogeneous of order m. If m is equals 1, so this is a homogeneous, so I have 1 over here, is simply lambda. So it's a homogeneous of the first order. Okay? Yes?
Can we just set like
Sorry, I cannot hear you. Louder.
Can't we just set instead in the summation, instead of saying the derivative, can't we just say AI, and AI is a series of constants?
AI is not a series of constants. So if I would write it like this, would it be more convenient for you? It's just a derivative, a partial derivative. And the partial derivative, by definition, is I'm using this as a variable, and all the other variables over here are constant.
No. Because it's a second, I'm saying the second derivative will have...
But it's not a second, it's a first.
It's a first, but if you take a second derivative...
I don't want to take a second
Yeah, but
derivative.
that's what I'm saying. Don't even have to put a derivative. You can just put AI and like a series of constants called AI.
But it's not a constant.
Not xi.
It's something. It's something. It's something. But it's a derivative of g with respect to xi.
You can just say it's AI instead of thing, and it's the same thing because then when you take the derivative...
Why do you say so? I don't know. So I don't know. But Euler haven't told me that this is a series of constant. You are right that if it's a series of constant, then it is satisfied. But maybe there are some other more complicated forms. Right? Euler tells us that this is the form. You're telling me no, that there is only constant form. So a constant multiplied by x1 plus a constant multiplied by x2. This is a homogeneous function of the first order, but it's not the only one. There is plenty of others. And this great man by the name of Euler proved that for all of them this holds. Okay? Nice theory. Otherwise it's trivial. I completely agree with you that if it's a polynomial of the first order, then it's simple. But Euler tells us something much more complicated. Right? He doesn't tell us, well, if G is a series of constants multiplied by x's, then you can write it like this. Yeah, this is trivial. You don't need Euler for that. He tells us, if G satisfies this condition, then you can write it as the following. Okay?
I just thought of another function.
Okay. That's good. Other questions?
מה שפשוט רשמת שם עם הלכל, זה אומר שפשוט קיבלת את כל היתר.
Yeah. I keep all the other variables constant. This is the meaning of partial derivative. Okay, so what it means for energy. Okay, so what it means for energy. For energy, this simply means, right, that E, what are the variables? S, okay, and X. So I can write E, not the differential of E, right? I can write E as what is this guy? This is dE to ds. What is this guy? I have here f1 dx1 plus f2 dx2 plus f3 dx3, right? This is what the symbol is. Now what is f1? f1 is dE to dx1. What is f2? dE to dx2. What is f3? dE to dx3. Okay. So from this form and Euler theorem for homogeneous functions, I can say that E equals to the derivative of E with respect to S multiplied by S. So I have D multiplied by S. Then I have the derivative of E with respect to x1, which is f1, multiplied by x1, plus f1, x1. Okay, I continue. I have here dE by dx2 multiplied by x2. But what is dE by dx2? Is f2.
F2 is not a constant, right?
F2 is not a constant. I don't really know what this can be dependent on many different things. It's not a constant. But the function is homogeneous, so I don't care. Okay. So in general, I write E as ds plus f dot d. Not d, but x. Right? And a specific form that we mostly use in this class or in thermodynamics, we simply write E as ds minus pv plus summa over I, mu I, and I. Yes?
Shouldn't energy have a constant initial value, like plus C?
So, well, we can introduce here for S or something. Okay. But energy is always extensive, and it's defined up to a specific value. Now, usually we say our energy is huge, and we have taken this constant to be something small, so it's negligible. We already neglected the interaction energy. So all of this constant we also somehow threw through the window. Okay? Yes?
למה יכולנו פה ישר להגיד, הפכנו את ה-TDS כששכרנו את הכל ל-TS? בגלל ש-T הוא קבוע אינטנסיבי?
No. So the question why I made this jump from here to here?
Yes.
Only because it's a homogeneous function. We know, and I'm using Euler theorem over here. Since E, and I proved it, is a homogeneous function, okay? It satisfies this equation. I can write it in this following form. Okay? I haven't done any integration. I have just applied Euler theorem. That's it. Okay. Other questions? Yes. If you could integrate and if they are constants, yes. But if they are not, if they are not constant, so you want me to say the following: let's integrate f1 dx1 and perform an integration. And you are saying this is f1 x1. No? Why not? It can be dependent on different other variables. Okay? Okay? So Euler tells us that if you do everything correctly, this is the form. Okay? This is what Euler tells us. Now, of course, this is approximately correct for large systems. Why approximately? Because we have neglected all different kinds of energies, and we said, well, approximately our energy is extensive, so we can use all of this. If you're going to apply this to microscopical small system, it won't work. Why? Because there the energy is not going to be extensive. Okay? So this only works for macroscopical objects. Now, we can start playing with this, right? We applied some theory, we applied nice form, okay? And we can start now playing with this form, maybe obtain other different formulas. So all of the thermodynamics that you have learned is basically games that I'm now going to perform using properties of derivatives, etc., when I'm playing with this equation. Okay, this is my equation, and this is my equation. So those two forms, this. And I have also dE equals to TdS minus PdV plus a sum of I, mu I, dNi. And all the games that you have, or formulas that you have derived in the class of thermodynamics, were connected to some games with this guy and this guy. Okay? So let's see, for example, something that is called Gibbs-Duhem formula. So let's start. We have dE equals to TdS minus PdV plus sum over I mu I dNi. Okay. I also can write that E equals Ts minus PV a sum of I mu I Ni. Okay. Let's take a differential over this guy. I take a differential from the left hand side and a differential of the right hand side. Okay? Let's see what we get. So on the left hand side it's easy, it's simply dE. On the right hand side what I have, a differential of Ts minus a differential, because it's a linear operator, minus a differential of PV plus a differential or sum of differentials of mu I Ni. No, we just want to play and see what we get. That's it. All of the different forms that you already seen in the teaching us in TA class, you've seen Maxwell relations, right? How we derive all the different Maxwell relations. We take this guy and we start to play with this using some calculus rules. There are enormous amount of different formulas that one can derive by playing calculus with this and that. Okay, so what we have over here, we have dE equals dt multiplied by s plus tds minus v dp minus p dv plus a sum over I ni d mu I plus a sum over I mu I dni. Okay, so this is the left hand side, this is the right hand side. By d I also know what it equals to this guy, right? So I can say all of this equals to TdS minus PdV plus a sum over I mu I dni. Okay. So let's move all of this to the left hand side, and this guy kills this guy. Okay. This guy annihilates this guy. This sum is completely annihilated by this sum, and eventually we are left with S dt minus V dp, okay, plus a sum over Ni d mu I equals 0. Is it important, this relation? Well, it's important. It has a name. It calls Gibbs-Duhem equation. And never mind how Gibbs and Duhem got it, but we see that by using some simple tricks, it's extremely easy. Okay. Now, why do I need this equation? Well, maybe it's going to be important for some specific gas or some specific system. Maybe it's not. For our purposes, we will use it in a second. Okay. But we see that small game with the differentials gives us some relation. Important or not, it's up to the experimentalist to decide. Why I need this equation? I want to define another function. So now we have an energy. Right? So the energy is very nice. I want to define another function. And it will be clear to you in 5 minutes why I'm defining this function for. Okay. But I want to define a function which I will term g. Okay. And it is E minus Ts plus PV. Okay. Okay. Why to do this? Okay. Why to do this at all? Okay. Well, because we can play game with this equation and see that this g is actually depends not on extensive variables but on something else. Okay. How do I know this? Well, let's take a differential of g. d of g equals d E minus Ts plus PV. Okay. So let's keep dg over here. And here I have dE. Here I have minus T ds minus S dt plus P dV plus V dP. Okay. dE, I know what it equals to. dG, dE equals to TdS minus PdV plus a sum over I mu I dNI. Right? So this is TdS minus PdV plus a sum over I mu I dNi. Okay, I also have these terms minus TdS minus SDT plus PdV plus VdP. Okay. Let's see what's left. TdS cancel out. PdV minus PdV plus PdV cancel out. Okay. Okay, so what I'm left with? I'm left with dg equals to what? Minus SDT plus VdP. Okay, plus VdP plus a sum over I mu I dNi. Now, from this equation, I already know what my variables are. Okay? G is called Gibbs potential. G is called the Gibbs potential. And I see that for the Gibbs potential, the variables are T, P, and Ni.
Why did it call it Gibbs potential?
He invented this. He is the first to perform this. Okay? Now, why have he done this? Why Gibbs? Okay, so he played with the formulas, he got some different relations, and he also went and defined this formula over here. So instead of using the energy, okay, he said, well, I subtract from the energy Ts, and I add here PV. Okay? Why Gibbs wanted to perform this transformation? Not to use energy for all his purposes. Why he wanted a function that eventually has a variables, not entropy, volume, and number of particles. He wanted a function that is a variable, that the variables there are temperature, pressure, and I. Exactly. Okay. So the answer here is those are quantities that can be used in an experiment. Now consider the following situation. I have a theory, great theory concerning about the energy of some specific system. Right? My energy dE equals TdS minus PdV plus sum over I mu I and I. Okay? And I have some theory. And I walk into the office of my favorite experimentalist, pick one, right? And I say to him, I have a great idea. My theory is based on the energy. And if you do this and that and this and that, you're going to get an extremely novel feature in the system. Okay? He asked me, Stas, what I have to do, what I have to think of, what parameter in my experimental system I have to modify. And I will tell him, oh, you just need to modify the entropy. He said, what's entropy? I said, entropy is a monotonic function that increases with the energy. He said, what's entropy? Well, entropy is sometimes, and we will learn it later, related to the number of microstates in the system. What's entropy? Entropy, you know, entropy. Stas, here's the door, please get out. Okay? We need, when we look on specific systems, not some general physical theories, when we look on specific systems, we need to use the proper coordinates of those systems. Okay? And it depends on what my experimental system is. Sometimes I can change the temperature, or I can change the pressure. Maybe this I don't need to change. Okay? So Gibbs wrote this function, or find this function. Why? Because he wasn't interested in dealing with the entropy over here. He wanted to deal with temperature, because usually for experimental system, temperature is something that is easy to measure. Right? I stick a thermometer into my system and it tells me a number. Great. I don't have a thermometer or a proper measurement for the entropy of my system. And we will learn it why when we will talk about statistical mechanics. Okay, but this is only one example, right? Can we do it generally, right? I have an energy, and the energy is a function of S, V, and N. Maybe I have some additional stuff over here. F1 dx1 plus F2 dx2. Is there a way of proper change of coordinates? Okay. Of proper change of coordinates. If I have a function which have a specific coordinate, what is the proper way to change this coordinate into something, okay, that I can control? So you actually learn this technique in analytical mechanics. And it's called Legendre transformation. Have you heard about Legendre and his transformation? Okay, so it's going to be easy. Yes? Okay, so you can show that. So the question is, what is the meaning of Gibbs potential? So two meanings. One, it is a nice function that we can work with. Okay. The other, it can be shown that G equals to mu I sum of mu I and I. So it's basically related to the chemical potential of your system. It's the energy that is based on the constituents inside your system. It can be shown, and we will show it later. What? Sorry? זה האנרגיה הכימית או האנרגיה של נוכחות החלקיקים במערכת. This is the energy. Gibbs potential describes what is the energy, or describes the energy that it's coming only due to the presence of the particles. רק כנוכחות של חלקיקים בתוך המערכת. Okay, so remember mu is a chemical potential, right? Mu is mu I dE to dNi. So I change the number of molecules or the moles of a specific species inside my system, and the response, or by how much the energy changes, so the rate, is the chemical potential. Okay, so questions now? Yes.
אבל אמרנו שה-G הוא לא תלוי רק ב-NI, כמו שאנו פשוט...
In specific situations you can show this.
בסיטואציות מסוימות אפשר אחרת...
Yes.
ובסופו אנחנו גם יכולים לשלוט כך שהיתרון זה שנוכל לשלוט.
בדיוק. אוקיי. Legendre transformation. Do you all know Legendre transformation? I need to cover this? No? Okay. Yes, all right. So, let's see if you know it. Okay, so let's assume I have y and x. Okay, and I have some function, y is a function of x. Y is a function of x. Okay? Now, I want to describe this function using a slightly different measure. Okay? What's the measure that I want? I'm going to a specific position. Okay? It's over here. Here I have an x. Here my y. So this is a specific point on my function. Okay. And I plot a parallel linear line that I forgot what is the term in English for mashik. Tangent, right. I plot a tangent line through my function at specific point x and y. Okay. And, well, lo and behold, I know that, well, the derivative or the tangents of alpha, okay, of my tangent. Right. So I know, well, when I plot it, I actually know what is this alpha is. Now, this is not completely enough. I don't need only the derivative, right? This alpha, or the tangents of this alpha, is the derivative of this function, y of x, at point x. Okay? I also want to tell you something about where my tangent is crossing the y-axis. Okay? So I know what is y and x. Okay? Y and x, and I'm now trying to use two different other quantities to describe the same this function over here. Okay? I'm using this as the tangents of alpha is, I will call it d, and it equals to y minus psi divided by x minus 0. Okay? Now, out of this, what do I obtain? I obtain that d multiplied by x equals to y minus psi. Okay? Or psi equals to y minus d multiplied by x. So I started with some function of y of x, and now I have a function of psi of d. Okay? So this is my transformation, and I have a function a of one coordinate x, okay? And there is an equivalent representation of this curve by using psi and d, okay? And the psi is a function of d only. Now you see what's the point of Legendre transformation. I obtained a new function and I somehow sweep the variables. Beforehand, my variable was x. Now my variable is d. What is d? D is the derivative of y with respect to x. Okay? So anytime I want to switch from one variable to the variable which is a derivative of the function with respect to the first variable, this transformation is called Legendre transformation. Okay? And D is a specific name. משתנים מצומדים, conjugated variables. Right? You learn it in analytical mechanics. Questions?
יכול לחזור על המשפט האחרון שאמרת, הקודם, לפני המשתנים
To
מצומדים?
repeat the last sentence, what was, I have a lot of sentences. What is the last one?
אמרת משהו על
אחרי
הצגות.
שפסאי תלוי ב-D.
כן.
Okay, so here I have a function of y dependent on x, and I create a new function which is alternative description of my curve, but instead of using x, I'm using the derivative of this function. Okay. That's it.
זה גם לי שאלה.
Okay, questions?
כן, אנחנו לא משנים את x במהלך התהליך הזה.
No, well, for any x we will have something else, yes.
אוקיי.
Okay, for any x we're going to have something else.
כן, אז גם y ישתנה ואז גם b ישתנה.
Yeah. Everything is going to change.
אז אנחנו בעצם מקבלים את x ואז מגלים את הטרנספורם לפיזי.
Exactly. So, what we have over here is that we have psi, a function of p. We have y, a function of x, and we know that dy to d, not d, dy to dx equals to d. Okay. Now, what is d psi? Remember that all of this thermodynamical potentials, thermodynamical functions, they are always differentials of something. Okay, so I have a differential of E, and I need to create something else, which is not going to be dependent on the entropy, but it's going to be dependent on the temperature and the pressure. Okay, or whatever variables that you like. So d of psi, it is d of what we have over here, y minus dx. It is dy minus d of dx. Okay, dy, we know what it is. What is dy? Dy is d dx. Right? So we are not in the math department, so we can use it. Okay, and sorry for all the mathematicians that are in the audience, but this is correct.
Differential one form.
Yes, differential one form. Don't mention manifolds, please. Okay. Okay, so d dx, and we have here minus d d, okay, minus d x dd minus d dx. Okay, this and this cancels out, and we have minus x d d. Okay, so we obtain the form that d psi to d d equals minus x. So in this way, right, if we have one function and it's a function of x and we want to describe or obtain an alternative representation, but not as a function of x, but as a function of a derivatives of x, right? We're performing this subtraction, and this subtraction is called Legendre transformation. Okay? Now we can do this for as many variables as we like.
טרנספורם לג'נדר זה הדבר הזה ששנת עם הפסאי D.
So, if we have a function of x1 and x2 and x3 and xt, okay? This is our function. The Legendre transform of y with respect to xj, the Legendre transform that I want to keep part of the variables, and I want to get rid of the variables from xj up to xt. Okay? Again, I'm keeping all the original variables x1 up to xj, and those variables are getting kicked out. I don't like them. Okay? I really don't like them. Not including xj, right? So psi is y minus a sum from k from j up to t dk x dk xk. Okay, so what is dk? Where dk is dy to dxk. Okay. As this function psi is a function of x1, x2 at x j minus 1, and here I will have dj plus 1 up to dt. X's are regular variables. These are conjugated variables. Don't worry, we're almost done. We're almost done. Now, how I can, so I now know how to relate d to the derivatives of y, but I can also, like over here, relate x to the derivatives of psi. Okay? It's the same way around. So x k equals minus d psi to d dk. In this way, you can go from one representation to another. So if I start with energy, this is an energy, and we do know, or at least we think we do, that we understand what energy is. Now, I want a different representation with different variables, okay, that I can maybe control. I'm going to use Legendre transformation in order to obtain those new generalized potentials. Okay, so Legendre transformation is a way to obtain generalized potentials. Why they are created? They are created so that we can use something to describe systems where we cannot control entropy or we cannot control volume, etc., etc.
Stas,
Yes.
I still can't quite understand why are we still, למה אנחנו עדיין כאילו מתעלמים מה-X ray ואנחנו עדיין צריכים עליו?
What do you mean? Well, you have to use it. So you need to you're asking me here. Well, I will going to have xk over here, and psi is going to be dependent on xk, right? But you need to express xk as a function of d.
Ah, okay.
All right. So xk, let's write it over here, is a function of all the different d's. Okay. So what are the different generalized potentials? There are many, and we are going to use only a few generalized potentials.
What do you mean by obtaining general potential?
What?
What do you mean by obtaining general?
Okay, I will give you an example. So I have E is a potential, right? An energy. I can call it a potential. And I subtract from it T of S. Okay? So this guy have a name. This is Helmholtz free energy. Helmholtz thought about it. Why? So remember, E is a function of S, V, and N. Okay? Now I perform this subtraction. E minus Ts. This is Helmholtz free energy. What are the variables of F? So T, remember, what is T? D to ds. So what I have done here, E minus dE to ds. It's like over here, right? I have dE to ds and S. So I'm going to have variables instead of S, I'm going to get T. The function of T and V and N. Okay? So I had an energy, and the energy was a function of extensive variables. I now have something that I really don't know what it is, right? I know it's some sort of energy. The first guy who did it was named Helmholtz, and we call it free energy in order not to get too fuzzy about what energy is. And it's a function of extensive variable V, extensive variable N, and an intensive variable T. Okay. we already seen Gibbs, okay, G, E minus Ts minus minus P, V. This is Gibbs. Gibbs free energy. Okay, so this is a function of T again, and P and N. And I will just write down the last two generalized potentials. We have H, which is E minus minus P, V. This is enthalpy. H is a function of S, P, and N. And we have finally psi, which is E minus Ts minus mu n, which is grand canonical potential. And psi is a function of T, V, and mu.
Stas, what is H again?
Enthalpy.
But Stas, how does this obtaining generalized potential?
So no, it's the energy, but it's the energy in different variables. Is the same? Is the system stays exactly the same? I'm just now using different variables to describe it. Right. Now you can ask me why it's important, and this I will tell you next week when I'm going to extend the principle of maximum entropy to the principle of minimum free energy, minimum Gibbs free energy, minimum enthalpy, or minimum grand canonical potential. So the next step after getting all of this is to obtain a variational principle to describe what can we do with the different energies, right? Because eventually we want to say when is equilibrium occurs, or what happens at equilibrium. And the principle of maximal entropy, or the principle of minimal energy, or minimum Gibbs free energy, minimum enthalpy, minimum grand canonical potential, is going to provide us a way of, okay, we look on the system, we change different variables, and we know where equilibrium is going to occur. Sometimes it's easier to change S. Sometimes it's easier to change T. Sometimes it's easier to change the chemical potential. Each system has its own properties. We will see it next week. Thank you, that's it.